Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll work out two numerical examples and later I'll explain how to check the validity of Euler's formula for a given column. Now let us work out a numerical example. Find the safe load using Euler's formula for an 8-meter long column with both ends fixed. The column cross-section is circular and has a diameter 80 mm. Given E is equal to 205 gigapascal, factor of safety is equal to 4. So the column is 8-meter long and its both ends are fixed. And the diameter is 80 mm. The Young's modulus of the material is 205 gigapascal and factor of safety is given as 4. So I tabulated the data here. Length 8 meter, it is 8000 mm. E is 205 gigapascal or 205 into 10 raised to 3 Newton per mm square. Diameter is 80 mm. Factor of safety is 4 and both the ends are fixed. Now let us work out. Now since both the ends are fixed, effective length can be taken as total length 8 meter divided by 2. 8 meter means 8000 mm divided by 2, which will give 4000 mm. So effective length to apply in the general formula, that is pi square EI by L square. You have to use this effective length because they are fixed at the ends. You have to find out the effective length as half of the length of the column. So 4000 mm here. Column is having a diameter 80 mm. So that means cross section is circular. So if you take the cross section, it will be circular in shape, solid circular cross section. And moment of inertia of solid circular cross section is pi by 64 d to the power of 4. Pi by 64 into 80, diameter is 80 to the power of 4, which will give 2.01 into 10 raised to 6 mm to the power of 4. Now Euler's buckling load is given by pi square A by L square, where L is the effective length and I is the least moment of inertia of the column cross section. So in Euler's formula, always you should use least moment of inertia. In this case, with respect to whichever axis you take, either x-axis or y-axis, you will have same moment of inertia. But rectangular cross sections will have two different moment of inertia with respect to x and y axis. With respect to which axis you get the least value of moment of inertia, that has to be taken as the value of moment of inertia in this equation, because when it is a rectangular cross section, it can buckle in two different directions. With respect to which axis it has got least moment of inertia, perpendicular direction to that axis, column buckles. So that value of moment of inertia, that is least moment of inertia, has to be taken into this equation. But in this case you have same moment of inertia with respect to both axes, which is pi by 64 d to the power of 4. Now pi square is given 205 gigapascal, so we have converted into Newton per mm square into I, the calculated value of I substituted, and the effective length is 4000 for this end condition. So you will get 2,54,251.47 Newton or 254.25 kilonewton. This is a load at which the column buckles or fails. It bends and it fails. Buckling means it's a failure of the column. So 254.25 kilonewton, the column fails or buckles, or this is a crippling load. Now you cannot apply so much load. You are given the factor of safety, so you are asked to find out the safe load. So what is a safe load you can apply? So this is a theoretical calculation of buckling load for this column. So we cannot exactly say that for this load it fails. It may fail slightly less than this load also. Maybe at 200 kilonewton it may fail. Maybe some imperfections or some small defects also causes failure at a very less load. So you have to take care of the safety of the column. So you need to always, any design, you need to use a factor of safety. You cannot allow up to the failure load. So if you want to reduce the load applied on the column by a factor 4, a factor of safety is given as 4. So you have to divide the buckling load by 4, which will give the safe load as 63.563 kilonewton. So this is going to be a safe load which can be applied on the column, which prevents the buckling. Let us work out another example. Find Euler's buckling load for a 7-meter long column with outer diameter 120 mm and thickness 20 mm. The column is fixed at one end and hinged at the other end. Given E is equal to 200 kilonewton per mm square. So the column is 7-meter long or 7000 mm. Young's modulus is given as 200 kilonewton per mm square. A kilo is 10 raised to 3. So 200 into 10 raised to 3 Newton per mm square. So kilonewton per mm square means it's a gigapascal, equivalent to gigapascal only. Outer diameter is 120 mm and thickness of the wall is 20 mm. So from this you can find out the inside diameter. One end is fixed and other end is hinged. That is the end condition. Let us work out. Effective length of the column for this end condition, one end fixed, other end hinged. Effective length is L by root 2. Length is 7 meter or 7000 mm. 7000 divided by root 2, which will give 4949.75 mm. So that is effective length. Now outer diameter is given as 120 mm. So you have to reduce the thickness on either side to get the inside diameter. So outer diameter minus 2t will give the inside diameter. Outer diameter minus twice thickness, that will give the value of inside diameter as 80 mm. Now this is a hollow section. So outer diameter is given, inside diameter is given. So the moment of inertia of the column cross section is 5 by 64 into d naught to the power of 4 minus d8 to the power of 4. A solid circular section, it is 5 by 64 d to the power of 4. So here 5 by 64 into d naught to the power of 4 minus d8 to the power of 4, which is equal to 5 by 64 into substituting d naught and di. D naught is given 120 and di we have calculated as 80. Substituting that, you will get the moment of inertia as 8.168 into 10 raised to 6 mm to the power of 4. Now you can apply the Euler's buckling load general formula which we have obtained, pi square EI by L square, where L is based on the end condition you have to replace. So in this effective length which we have calculated has to be substituted for the given end conditions. Now E is 200 kilonewton per mm square, so we have converted into Newton per mm square. I we have calculated, okay, that you can substitute, and effective length. So substituting that, you get 6,58,092.4 Newton. That is the buckling load for this column. So we can convert into kilonewton, 658.09 kilonewton. That is the buckling load. So at this load the column buckles. So this is only a failure load or buckling load for this long column. Now if you are going for a design, safe load you have to calculate by dividing by factor of safety, but you are asked to find out the buckling load for this long column. So they have given it as a long column, so you are directly using the Euler's formula. You need not check whether the formula is valid or not, or whether it is a long column or short column. If it's a short column, then you have a different equation to calculate. This load will be usually less than what is given by a short column. So this since the problems which you worked out, they have directly given it is a long column, so you can always use Euler's formula without any checking. But how to decide whether the given column is a long column or short column? So that we will see. Now, to check the validity of Euler's formula, whether the given column is a short column or long column, or whether the Euler's formula is applicable for a given column, how to check that? Now we know that for a short column, the failure load is PC is equal to sigma Ca. So the failure load, the crushing load or the failure load is sigma Ca. So sigma C is either yield stress or failure stress of the material. So the load PC that for a short column, the failure load is sigma Ca. That is the stress at which the material fails, yield stress into area of cross section. That will give the maximum load this column, short column can support. But when it is a long column, it fails at a load less than that given by this. Even if long column is having the same cross section, when the length increases, the chances of buckling is more. When column can fail due to buckling, and that buckling load will be less than the load given by this short column. So for long columns are likely to fail for a load less than this load. Now how to check whether the given column is a long column or short column? Buckling load given by Euler's formula is pi square EI by L square. Now to check whether the Euler's formula is applicable, long columns will have a failure load less than the load given by this short column. Okay, so when pi square EI by L square should be less than or at the most if it's equal to sigma Ca, you can say Euler's formula is valid or it's applicable. So this is a crippling load given by Euler's formula. It is applicable only for a long column, and this is a failure load given by short column, but long columns will fail at a less load compared to a short column. For short column you cannot apply Euler's formula. Okay, so for Euler's formula to be valid, pi square EA by L square should be less than or equal to sigma Ca. Now pi square EI, I you can replace by AK square. Okay, so pi square EI by L square, I replaced I as AK square, where K is the least radius of gyration. Since I is the least moment of inertia, K is the least radius of gyration of the column cross section. Radius of gyration is root of I by A. From that you can write I is equal to AK square. So substituting least moment of inertia as AK square, you get this equation. So this is when Euler's formula is valid. So now a common factor on either side you can cancel, still the formula will be valid, the inequality will be valid. So you can cancel it. Pi square EK square by L square should be less than or equal to sigma C. Now if you equate it, that is, so when they are equal, also you can apply Euler's formula. That is a point where Euler's formula is still valid when you equate this. Okay, so by equating you get this expression pi square EK square by L square equal to sigma C. I am equating this for limiting case. For limiting case, for Euler's formula to be valid, you can equate that. Okay, so when this is less, it is valid, but when it is equal to sigma C also, it's valid. That is a limiting case. Now I rearrange this equation by taking K to the denominator. So K square I have taken to the denominator. You will get L square by K square or L by K square. Pi square E by L by K square is equal to sigma C. So this is a limiting case. Now by rearranging you will get L by K. L by K square is equal to pi square E by sigma C, or L by K critical value. So I will just put it as critical value because By equating, you got this value for L by K. So that is a limiting value or critical value for L by K. Now L and K are variable. So length of the column and least radius of gyration depends on the column. Whereas right hand side properties are material properties, that is fixed for a given material. So this will give critical value of L by K, and this is a purely a material property. So right hand side is purely a material property. So critical value of L by K, it's constant for a given material. Now columns made out of this material can have different values of L by K based on its physical dimensions. Based on the physical dimensions means based on the length, cross-sectional area, the shape of cross-section. L by K will vary from column to column, which is made out of this particular material. So if a column made out of this material and which is having a value of L by K less than this critical value given by this equation. Critical value you got by equating this. So if the value for the given column is less than the critical value, so this denominator will decrease and left hand side will increase. So Euler's formula will not be valid. Left hand side should be either less or equal to right hand side. That is when Euler's formula is valid. So L by K cannot decrease than this critical value. L by K of the given column cannot go below this critical value. If it's below the critical value, Euler's formula will not be valid, and you can classify the column as a short column. Whereas the L by K of the given column based on its physical dimensions made out of this material is more than the critical value, then left hand side will decrease and Euler's formula will be valid, and you can classify it as a long column. So for a given material, the critical value of L by K is only depends on the material property. And now using that material you can make columns having different physical dimensions, and based on that physical dimensions you can calculate the L by K, which is known as slenderness ratio. If you calculate L by K, if the value of L by K for the column made out of this material, if it is less than this critical value, it is a short column, and if it's more than the critical value, you can classify it as a long column. So for Euler's formula to be valid, whatever L by K for the given column, that should be either equal to this critical value or greater than the critical value of L by K. And L by K is known as slenderness ratio. How slender the column is. Length increases, it becomes slender or thin. But K also you can take into a factor. K is the radius of gyration. It depends on the cross section. If a cross section area decreases, K decreases. Even the cross section area distribution also decides the K value. So if the K is less, it becomes slender. Okay. For the given length also, if a K decreases, it becomes slender column. So for example, a matchstick you can consider as a slender column. If it is applied compressive load, it buckles and fails. Even though the length is less, it cross section is small, and the material properties also decides, because critical value decides on the material property. So critical value of L by K is purely a material property which you can get from using this equation, which you can calculate using this equation. Now you can decide a column whether it is a long column or short column based on the physical dimensions of the column. So you calculate the effective length divided by least radius of gyration. for a given column. Let's say, suppose you get the L by K of the given column as 200, and if a critical value of L by K based on the material property is 150, now for the given column it is 200 is the L by K, or slenderness ratio is 200, whereas critical value is 150, and the column is a long column, and you can apply Euler's formula. Suppose another column, if you make out of that same material, and if you have that L by K for that column based on its length and the radius of gyration, if you calculate L by K or slenderness ratio, if you get 40 as a slenderness ratio, that is less than the critical value which based on the material which you have calculated as 150. So that is L by K of the given column is less than the critical value of L by K for the given material. So then it is a short column. You cannot apply Euler's formula. So critical value of slenderness ratio is purely a material property, and now the slenderness ratio of the given column is less than the critical value. The column is a short column. And if the slenderness ratio is greater than the critical value of slenderness ratio, the column is a long column. Comparing the slenderness ratio of the given column with the critical value of slenderness ratio given by the material property, you can decide whether the column is long or short. That's all for today. Thank you for watching.